Ok.
brasileiros. Aposta 205 milhões.
of Engineering at Texas A&M University, College Station, Texas. His interest areas are automate assembly system design, control, integration, diagnosis, and preventative maintenance, optical infrared image for product process characterization, and failed prediction, micro nano and manufacturing e design of technology for automation in robotic education. He has been awarded several grants totaling over $5.5 million, and he published approximately 200 articles in important journals and proceedings. Dr. Shi receives the PhD in Industrial Engineering with a minor emphasis in computer science from Texas Tech University. He was named Honorary International Chair Professor for National Taipei University of Technology in Taipei, Taiwan from 2015 to 2023. At Texas A&M, he was named Halliburton Faculty Fellow in 2005, Halliburton Professor in 2011, and William Montini Head Fellow in 2014. He also received a National Science Foundation Career Award in 2003. So, it's a great pleasure to receive you here. Thanks for coming. I would like to thank PAPESP and the Texas A&M University and the INCT SAC for supporting this visit.
Howdy. In Texas, Texas A&M University, our building is called Howdy, similar to. So Texas A&M is abbreviation of agriculture and mechanical. A while back, we, as a land grant university, so start with agriculture and mechanical. So when I arrived in Sao Paulo, and I took a ride from Sao Paulo to San Carlos, and I noticed that one of the biggest, perhaps, perhaps the best economy is agriculture. So we have something in common. Although we all go beyond agriculture, right? So we are better than before. However, the knowledge and the skills which you are doing can always apply in agriculture to make that industry even stronger. So today my talk is, I understand I better share with you some of the senior professor that I really appreciate you attend these meetings, and I understand that my knowledge may not as in depth as your expertise, but I will give it a try in this area, and I welcome for the comments which you might have. So the topic is on cyber physical systems and cyber-enabled manufacturing, Industry 4.0, and some of the definition, perspective, and what are the future holds. Yes, can you hear me? All right, I was afraid to create an echo, so I intentionally moved away from my mouth. All right, so we're going to introduce some of the concepts like CPS, CEMS, and Industry 4.0, and then look at what does it look like, what has been done, and what can be done more. And I will share some of the experience we are doing in our lab. So I understand most of you probably already know what a cyber-physical system is. Here, just briefly introduce our concept one more time. You start with the understanding workshop, and then it's called present the cars to cars of 60 or 80 students. So I think this is better, right? Is it? All right, so what is a cyber-physical system? So use the systems, they are connected together. They will have sensors, actuators, and processors. And the point of these components is interact with the physical systems. The intent is make the system more efficient, accuracy, perhaps some environment you don't want it to be in, and you can use this concept to achieve those purpose. So we translate our definition in this diagram in a way it's easier to understand. So you have a physical system on the left, and your cyber systems on the right. Your control system on the bottoms. So inside your physical systems, you're going to see different types of sensors. You can form this sensor into a network, and that will generate data. So your data will go from one side to the other side through the wireless communications protocols. And you have cyber systems which can be presented as a model. In that model, you can do experimentations, you can do predictions, and you can generate some knowledge based on the data which you retrieve from the physical systems. And our knowledge can become useful. And you put it into your control systems, then you can do a real-time approximately to adjust your process parameters. Then the intent is what? The physical system performance will be better. Okay? So you can prevent some of the potential error. For example, you are making CNC parts, titanium parts, using CNC machines, right? So that's a very expensive workpiece. So if you notice that your spindle, your cutting tool is getting too hot, right? So you as an expert, you can adjust the coolant, the volume of the coolant more, or you can lower the spindle speed. But if you want a machine running 24/7, then you need a sensor to feedback this information to a cyber systems that do the preventive maintenance. And then that feedback to control systems say, hey, we need to do something about the drill bits. Perhaps we need to replace it. Perhaps there's no coolant in it. So on and so forth. The intent is what? Your finished product will be great. Okay, so that through the concept of cyber physical systems, you can achieve that. So some of the benefits of CPS, including the quick response times, you can do a very precise and accurate predictions, and sometimes you can enhance human performance. For example, if your process has a lot of process parameters, right? I interviewed a few experts in chemical industry recently. They have the operator looking at control panels. So these are the operator looking at control panel, try to make sure the oil refining process is adequate. But if you have so many parameters you need to look after, and I learned every shift for them is 12 hours looking at the panel, and then to make dynamic adjustment. It's more than 100 parameters. And so you can be a very good experienced engineer, but you want you to interpret the data with 100 parameters over the period time of 12 hours or 1 hour. It's almost impossible. So we can use the CPS to enhance the argument human performance. We can put AI into a cyber-physical systems, do the data minings, right? And then feedback to control systems and make the adequate adjustment to process parameter. Therefore, your process can continue to run. So those are the potential benefits of we call it cyber-physical systems. These are some applications which has been applied, and it's not limited to this application. It can also be others as well. It's you decide where and when it can be applied, as long as you know the concept. The first one is what? The cybersecurity. We call the cyber online security. You can do search and rescue, right? So your drone itself can be a sensory device. Your physical system can be the search area, right, which you want to navigate and collecting the data. And then your drone has a sensory data feedback to your operator now can act as a control systems and then to decide what to do next. So now we call the search and rescue. It can be applied in transportation as well, assuming you have a fleet of autonomous trucks. How do they translate? How do you collect those data of each vehicles and fit it into a cyber systems? Therefore, that can generate knowledge. What is the best maintained distance between the vehicles? And what time and when, and then through the central controller to forecast the real-time information to vehicles. So those are things can be also applied in transportations as well. There are other applications, right, in the healthcare and also other in agriculture. And one of the projects we did is the smart irrigation systems. In Texas, we often will have drought. It's probably, within Texas, we have a high percentage of drought. And the question is, how do you use best use of the water? How do you, and if you do the math and calculations, maybe more than 60% of water is used for farming. So how do we save our water? So the concept is, can I provide the right amount of water to the right region of the farm at the right time? So later I will show to you the smart irrigation system, which we have done a little bit about. We can also apply in manufacturing. It's specifically, how can we make the manufacturing sector, which perhaps is most profit-driven industry that can help the country to grow in addition to agriculture, right? How do we, those are things that we can apply cyber-physical system for. So this example is what? The air, we call it air traffic controllers, right? So yeah, so many aircraft got delayed by the weathers, and how do you have a cyber system can help you to schedule how long you want to, each one should come in, each one should come out. Those are things and been proposed and funded by National Science Foundations. And the smart city, right? A smart city in the sense of, one example is the mass transportations. The bus in Taipei, you go to every single bus station, you will see which which bus number is coming, where does it go, how long you have to wait. Every single bus, you have beacons that send out the data to the cyber systems, and that will control how fast that bus should run and from where to where. You can also apply for utilization of water within the city and so on and so forth. The drone, I think I mentioned this earlier. And this is how can we use cyber physical systems to help disabled individuals to recover quickly. So, all right, so what are the open things, open problems can be solved? Imagine if you are in a music concert hall that had 20,000 audience, and you as the singer, you want to hear everybody's voice, and how would you do that? So everybody has a cell phone, that's a note. If you go to 50,000 notes into a network, how do you process that amount of data and give you a consensus feedback? So we call it challenging or what? We call it scaling up. Right? The other one is security and privacy is always an issue. You don't want the hacker get into your cyber physical system, not controlling your manufacturing processes. I think one thing I'd like to point out is in the manufacturing sectors, there are not many applications that are being developed in the manufacturing sectors. And perhaps it's perception, perhaps it's a cost-driven. And I will give you some examples and give you some thoughts. So I want to switch the gear a little bit to cyber-enabled manufacturing. What exactly does it mean? What does it look like? Traditionally, this is what a manufacturing process will look like. You will start with raw materials, right? And you will start with equipment. You fit into your processes. Processes can be packaging your produce into carts. You're going to have good parts, you're going to big parts, and you will have control systems that can be programmable logic controller driven to do the packaging of your produce. And that is a traditional way of doing it. In the case of cyber-enabled manufacturing systems, this is what it looks like. You replace that physical system in the middle with the manufacturing systems. And then your input is going to be raw materials, equipment, and your output is what? Good quality of products and time it takes to finish it. Right. And then you're going to have what? Sensors and sensor network. That part is the most difficult part. And that part is what we found when I interviewed with manufacturing companies. They say, well, we are still using programmable logic controllers. We are still trying to figure out how to automate entire processes. So now, in other words, we are still in industry 3.0, which is programmable logic controller for automations. How can we get to Internet of Things? We don't even know what does it look like. We don't even have engineer has our skill set. So those are the common comments we interview industry, and those are the feedback they give it to us. They also say, we have a lot of data. I don't know what to do with that data because we have CNC making parts every single day, 7 days, 24/7. We don't know how to get the data out. Then how do I use that data? So these are the common problems. But there are always a way of doing it. It's just a matter of how you approach the problems. I'd like to give you some example here, which has done in manufacturing domain. Some of you might be familiar with additive manufacturing, and one of the major driving is selective laser sintering method, right? In making the metal piece using the powder. And how do you control our processes? Therefore, you will not have any, we call the debond and thermal stress issues. And those are the things which has been applied using the cyber-physical systems approach. These are the common problems within the cyber-enabled manufacturing systems. And these are the results from the NSF workshop on some of the issues. I'll start with the architectures. How do we build our architectures? Like, how do I start? Start with, let's say, CNC machine as an example. How do I build around? CNC has the controllers, and how do I build a cyber-physical system to get the data out? And where do I put the sensors? So perhaps one approach is you have additional controller, right? And you understand what most percentage of the parts failure, right? Perhaps is the coolant is not enough, perhaps the spindle speed. So you add in those sensors and connect to the separate controllers, right? And then from there, you also have a measurement of how good is your parts, right? So you have inputs come in to your controllers, and with that data, you do the predictions, say, hey, it's getting too hot, it's going to have failures. So then you feed back to your controller, to your CNC code, say, hey, I need to reduce my spindle speed. So there's a way around it. We just have to be creative by adding additional controller, perhaps that's needed. Or the best way is what? Talk to the vendor, say, hey, how can we work together so I can buy more equipment from you? They open the controller architectures so you can tap into the I/O points and start to interface the needed sensory devices, and then they continue to improve that process. So those are the ways that we can solve the problems. Again, so architecture needs to be developed. And then, of course, there always how do we maintain the data securities, right? So I'm not an IT folk, so I don't want to talk too much, but it is a concern. The software, right? The software also needed. One of the things which we heard from industry when we interviewed them is, well, I'm using these CNC machines from this company in Switzerland, and they have their specific CAD and CAM software. But their CAD and CAM software does not work well, does not do if I create a drawing in AutoCAD and I fit into their software, does not always 100% accurately translate that CAD into the CAM code, the CNC code which I need. So there is a software compatibility issue here. So perhaps an open problem is what? The software which universal application that reading all different kinds of what? CAD software and generate CAM code, CNC code, which can fit into most of the CNC machines. So those are the areas which can be done for the future to make the concept easier to implement. All right, so there's another concept called Industry 4.0, and again, this concept starts from Germany. During the annual Hanover conference in Germany, I think it's Frankfurt, and they say, well, CPS is not good enough. we are in the age of Internet of Things and Internet of Service. So can we add those two elements to it? Then they call it Industry 4.0. And so this is the diagram for Industry 4.0. Instead of 3 block diagrams, now we are adding 2 additional components. One is Internet of Things, the other one is Internet of Service, which interact with what? With your control systems and interact with your physical systems. This is what I envision, or most people envision, what need to be done to reach Industry 4.0. Start from the very bottom layers of the architectures is your sensor. Your sensor has to be what? Network ready, right? So then we can form each sensor as a node into a network, and then we can easily what? Accumulate and integrate the data. That's the first layer. The second layer is the controllers, right? So your controller needs to be what? Ethernet ready, right? So that means allows you to go through the common protocol to transmit the data from the smart sensor through the controller into the network. So that is your network protocol, right? Your network protocol has to be compatible across many different applications. So these are what I see. It's 3 layers of technologies need to be enabled, to be ready for Industry 4.0 to be successful. I mentioned this earlier, right? So most of folks still say, hey, we are still in 3.0. We are still using programmable logic controller for our automations. And we do, the 4.0 is including CPS, Internet of Things, and Internet of Service. And what's inside the 4.0 mainly is you have lots of data, right? You have collaborative robotics, called robots, which work side by side with humans. You have augmented reality, which will facilitate the engineer or the operator to do their job better. Some example, let's say your car somehow got broken in the middle of the road. What would you do? In US, we call AAA. It's a towing company. They come and tow your car. Perhaps in the future is you have a smart glass, and then on here, on the top right corner, there's a lens that has Wi-Fi connections, and what? You communicate with the maintenance company. You say, okay, look at the engines. So your eyes look at the engines. At the same time, what? The images transmit back to maintenance company. At the same time, you will show the schematic of the engines. So what does that say? It will help you what? To diagnose the system failure much easier. So that's called the, we call it augmented realities. Another application in the industry, manufacturing, is I'm doing the testing of a lot of, nowadays, I think I was a Flextronics, the biggest world electronic manufacturing in the world. We call Flextronics. So they make electronics board for various industry, including automotive. And so it's so secure that your hand cannot touch the board because they don't want the board to be contaminated. And then, but that board has so many components. It allows some of the through hole, some of the service mount. To build a board, I heard, and I interviewed them, if there's a failure, you know what they do with the board? They scrap it. And then because they say the board is so essential, so important, you cannot manually fix it. Because in the process of manually fixing it, you might introduce other faults. So in this case, it's better you fix the problem before you go to the end of the line, right? So would it be better for the operators that when the parts arrive in front of you, your eyes look at the parts, it prescribe you the right work instruction, at the same time, make sure you put in the right part there. So step by step, in the end, you have good parts. And the other aspect is I think if you do wireless, then you have what we call the cloud computing, right? And how do you process those big amount of data, and of course the cyber-physical systems. Are these the only technology involved? No, it's more than that. But these are the common ones which people think can be useful. All right, so we talk about we talk about cyber-physical systems and cyber-enabled manufacturing, and we talk about Industry 4.0. And from the manufacturing perspective, industry perspective is, okay, how do I do it? Right? I know it is good, I need to get there, but how do I get there? How much investment I need to put it in? So perhaps this is a roadmap. You start from making a machine which is smart. And when I say smart, I'm referring to flexible. So in other words, my CNC machine is not only doing the milling, can also do the turning, can also do deburring. So I can reconfigure the mechanical structure of the machines and they perform different types of performance. They're multifunctional and robust and resilient. That means what? That means it's not prone to the failures. So you might have a duplicate redundancy controllers. If one of them fail, then the other one continue to process. So similar to in oil refining industry, you see that their process will have dual safety controllers. And they're running the same programs. If one of them fail, the other one will pick it up. So the process continues. So if you have a group of small machines, then you can put them together, it becomes a work cell. So you have small assembly systems, small robotics, and then you can make it as a work cell that will make a greater contribution. If you have multiple work cells, then it becomes what? It becomes assembly lines. And so I see the roadmap is start from one single machine that has the greatest potential, that has the greatest problem. You focus on that one, identify the problem, identify the causes of the problem, you retrofit the physical system with sensors. It makes no sensor become what? Network. And then what? You will develop an analytical model of your cyber systems, right? And then you do what? Do appropriate predictions in terms of what? In terms of thermal stress, right? In terms of the strength of the material which you are building, and then you adjust the parameter on the control system to make sure the workpiece will fit into your demand. Right? So the rest, I will give you some of the project we did, introductions. So we start with human comfort. Think about this auditorium. We maybe have 50 people here. Everybody's feeling about comfort is different. A good example is your car. In the past, there's only one nozzle, one AC control. But some of the car nowadays, you have two sides. One is the passenger side, one is what? The driver's side. Both has a nozzle to control what? The valve, the openness, right? And the intent is what? The thermal comfort. So one of my PhD students was working on was start with individual workspace, then what? Then auditorium types of workspace, and the cubicle type of workspace. How do we develop CPS systems to accommodate the human comfort at 3 different settings? One is one individual room, the other one is a cubicle types of settings, the other one is a large auditorium type of settings. So those are the things that my PhD student has done. So parameters including what? Temperature, activity type. Okay, in this classroom, in this auditorium settings, everybody is what? Is studying a lesson. So there's not much activity. Maybe in the room, everybody is doing watching a movie or playing a card game. So it's different. Different activity, you generate different amount of consume different amount of energies. Then your thermal comfort might be different, right? So, and we start with the window types of HVAC. And how this is a commercially available ACE. How much time do I have?
You have time.
Okay. So we start with a window unit. I think that's a common one. And we pay $50 from Walmart. Walmart is a grocery store, the biggest one in the US, next to Amazon, I think, or Costco. Anyway, so we follow a window unit, and then we add our controllers, Arduino controllers, and we are sensors. Then we start to build our cyber-physical systems, and we try to feedback to our control systems. And the point is the setting, the set point, and the fan speed on and off. These are the control the parameters for the physical systems, right? And then these are the measurable parameters for individuals. Think about if you stay in the hotel. If you stay in the hotel for some reason, you will, let's say the conference lasts for 3 or 4 days. And then some of hotel, they say they have a smart set point systems. Do you know how it works? No. Because every time you make adjustment of the settings, you record it. Okay, at the same time, it's also when and how often you make adjustment to the setting points. The intent is to collect that data. And then what is it? Collect data will help. It helps you to understand your preferences. And then from there, then you will prescribe the preferences to you. And of course, if you make adjustment more, then you have more data points. In other words, if you stay in that room for a longer period of time, you have more data points. Then the system itself can learn your behavior better. Okay, so the concept is similar that you can apply for a smart HVAC system. The difference is right now we make the controller visible to you. Right? In a hotel, you don't know where a controller is, or is a controller. And then also, what is the algorithm behind it to control, to fuse these parameters together and to derive the control parameters. That is the difference. Those parts is the one that you have to do experiment, the one you have to base on your theoretical understanding of the phenomena, and then to make the cyber system as close to the needs as possible. So that's what we did. The Pew paper was published. Okay, so I'm going to fast forward. So we do use machine learning method to do predictions. All right, now the next topic is on additive manufacturing. So we want to build a part. we want our parts will give us the right amount of strength that we needed. At the same time, it will prevent the thermal stress. So in the additive manufacturing, you might notice, specifically if you are using PLA or ABS, right? So you build up parts layer by layer by layer. Right? So the common problem is in between the layer, there is what? The bonding is not great. If you work in aerospace industry, you might notice it is the same process as they build the fuselage. It's fiber composite materials. It's a layer after layer after layer. Okay. If there's a bubble in the layer, if the temperature distribution of heating those layers of composite material are not even, then you will have a problem in the long term. So now the question is, how do we control it? And how do we get to that point? So this is what some of the techniques we use. Right? So the first one, in additive manufacturing, there are two things. One, we do the cell monitoring. One is, we call it error recovery. So when you post-process that CAD drawing and slice layer by layer into a CNC code that will move your nozzle from point 1 to point 2, in that process, you might have introduced some errors. The error in terms of position of your nozzle. And that's a common problem within the CNC industry is I have a perfect CAD drawings. When I translate it into CAM, somewhere, somehow, there's a tiny segment of code is not right. And you have to go to manual debugging to know which one. And it's just very time consuming. Because you have to understand the code, at the same time you understand your CAD, so then you can do the match of both. All right. So the idea of here is what happened, there is a mistake. Right. If you are making deposit of the droplet into your workpiece, somehow instead of 0, 0, you go to 0, 1. Right. So the idea is we want to spot that error, at the same time make a recovery. Okay. So these are the technology which we employed. So we have two cameras. Infrared camera is about mid-wave, 3 to 5 microns, looking at temperature distributions. Webcam give us a visible images of the actual coordinates. FEA is the one, the final element analysis. Some of you do the mechanical part design, but FEA allows you to, as long as you know the property of the materials, you know the boundary of the materials, then you can build the simulation models. Right? You build a simulation model to predict what happens. And here, the FEA, some of you might say it will take a while. It will take a long time to build FEA model right. So the concept here we have, it was not written here, is the FEA library. Is we build library ahead of time. So when we look at the drawings, we retrieve the adequate components of the library as a starting point, as a basis for us to model the cyber-physical systems. Otherwise, if we want to use our data, real data, to build APM model in the real time, that's almost impossible. So the way we approach this problem is we have to build a library or APM model with different shape ahead of time. And then in the cyber systems, then you look at the CAD and you retrieve approximately similar shape of the workpiece from the library and use that to continue the building of the cyber systems. After that is how do we make adjustment to to our control system, which actually moving. In other words, how do I make my CNC code flexible enough, therefore we can change the coordinates of the CNC code. In other words, our CNC code, our coordinates become a file, a text file, which we can dynamically change our text file and put it into CNC code. Therefore, we can do the adaptive control. And so that's how we did for the additive manufacturing and to do the monitoring and self-error recovery. And there's a video, okay, but I was not here able to play for you. But you can see that video. That's a video camera looking at, and this is the sensor. We're looking at the optical images. We identify these two feature points. Then after that, use that as a reference. We can identify the location of the nozzles, and then also the actual position of the nozzles. So we can do a comparisons. The first one, as I think I pointed out earlier, was to build the part that has the amount of strength, right, that we needed, because as I pointed out in the additive manufacturing, the fuse deposition method, the common problem is debonding. How do we avoid that to happen? In other words, we also found out the temperature distribution of the nozzle temperature as well as the chamber temperature as well as the workpiece temperatures has a significant effect on the thermal stress. So therefore, in our systems, we try to have sensitive device to monitor the temperature distributions of those three different areas. And then we feed those data into the machine learning models, and so we can predict the mechanical strength. At the same time, we can also, to avoid the thermal stress, we can control the temperature for the nozzles, for the bed, as well as the chambers. So we even retrofit the system with additional cooling devices. For example, if it's too hot, how do we cool it quickly? What you're seeing this here is an infrared camera looking at the nozzles of temperature distributions. And this is the workpiece which actually built. This is the 2D model, FEM models. So this one probably is the most one you'd like to know. Irrigation systems. How can we provide the right amount of the water for the right part of the field at the right time? So our idea is this is the irrigation systems. It's all moved in one direction. And for each section, you have nozzle that dispense the preset amount of water all at one time, regardless. So our idea is, can we have a robot which hang over these irrigation systems and go to every single area of interest, and then will probe the temperature and the humidity and the pH value of the soil. And from there, we'll deposit the right amount of waters. Where's my design? I missed that. So what we did is we have a robot similar to that. It's not on the slide, I apologize. It's like a cable robot. You think about when you watch the football game, how can you see the field of the football field so quickly? Because it's a cable camera will flying around the field. So if you use that concept, that cable is your irrigation system mainframe, and that camera is your robot. And then your robot will have a drilling device, and that drilling will drill a hole to your soil. At the same time, the tip of that drill bit will have pH sensors, humidity, and temperatures. So then that robot will wireless transmitter out to the post, and you determine how fast. Or can be the local controllers, just right on the robot, and then that determine how long the nozzle to be on for that specific region. So that is the things we did. The last one here is more on manufacturing setting here, is how can we make, this is a dual robotic assembly arm system. This is arm 1 and arm 2. These are conveyor systems. These are the sensory device. You can program it to see the input and output and voltage readings. This is the remote web server. So webcam allows you to see the real systems. Here is what? The simulation models of the systems. And here is the sensory devices. So we are using this Internet of Things and technology to help us to do the diagnosis of the systems. And this is what it looks like here. There is something I like to point out in the abstract, is this slide here is one of my master's student thesis. Oops. Oh. It's traffic lights, adaptive traffic light control systems, which we apply the psychophysical system to it to make that light become adaptive. In other words, so in this system here, your physical system is a traffic light. Your cyber system is, your physical system will have sensors on the pavement, will have camera looking at the traffic conditions of the intersection, as well as the how many pedestrians waiting in the queue. So those are the sensory informations we feed into CNN and ANN, and to predict the traffic conditions, high, medium, and low. And from there, we go through this multitask programmable logic controller to activate different timing routines based on the traffic conditions. So that's the overall concept. And the paper is under revision for sensor journals. And I think that's, I promise I want to talk about. So I think I'm done with the talk, and I welcome you for comments, suggestions. Again, I want to point out many of you are the expert in your field. I'm not an expert in your field, and I just present a little token of what I know, and I understand it's not perfect. And I thank you for your comments, suggestions.
Question, please?
Thank you, Luther, for your talk. I have a question regarding one of the slides that you presented.
Yes.
Where you show, I don't know if it's your vision or Advantech vision, where you present the layers that we have.
Yes.
In 3D.
Yes, I think that's from the Advantech. Yes. That's
Yeah,
right.
yeah. My question is it Advantech vision or is it your vision? Because in my opinion, we shouldn't respect this Industry 3.0 layer distribution, would it be not better to access directly the sensors if I wish?
Yes, it's possible. Why not? Why not? I think that there are advantages and disadvantages, right? If you you have a sensor network, you can know the condition of the sensors, right? But if all you want is a data, why I need to form a network? That's a good idea. I mean, so it depends on your needs. It does not need to be, you can go directly from your sensors, but also come back to how it will process those data. I think that's, so yes, you're right. It's not necessary need to have a network. Network is convenient in the sense of if you want to remote access to it.
Yeah, but maybe I expressed myself wrong. How could I configure my network so that I have direct access?
How to configure your network, therefore,
For example, I think today industry, they don't allow it.
okay, I'll sit down. I'll go back to the, go ahead. So since the industry does not allow you
To go direct to a machine and take
Okay.
the infos from one single sensor. But let's say a CNC machine,
that's right, that's
okay?
right,
Siemens PLC.
that's right.
If you want to know what's the temperature of your,
Yes, so I mentioned earlier was two approaches. You approach them with collaboration efforts, see if they can open it, or you have to retrofit yourself with additional controller. So I talked to this matrix industry. They are biggest. They are probably the bigger system integration company. When I say system integration company, you can call it machine builder or system integrator. So they build automated systems for specific industry needs. And I asked him this question. I say, hey, I have these customers in Bex manufacturing in San Antonio, Texas. And so they said, we can even get data out. And I said, yeah, you can talk to the CNC vendor, ask them to open it, or you add additional controller and then have your sensor connect to that controller. But I see that in fact, I gave a talk in 2016 as invited by Taiwan government of economy bureau. So we're looking at intelligent manufacturing. I'm the area which I think we in that seminar or workshop, they are CNC company. In fact, Taiwan is one of the industry's tool machining, so they make CNC machines. So they do say, hey, we do have intent to move to Industry 4.0. In other words, they are looking at the same pie. I mean, it's a big pie for everyone. So whoever can get it earlier and cheaper, they will take the market share. So they do have an interest. So they do. So I do see Siemens or even Hess machine in US. They do have. I did approach Hess CNC machine in US. Publicly, they didn't tell me yes, but publicly they are doing it. So there's sometimes a conflict of interest, but anyway. So.
Any more question?
I'd like to ask a question concerning the applications for smart agriculture.
Yeah.
You mentioned that you use hanging cables for a determined area, agricultural area. I was wondering, maybe you gave the example concerning the football game and the stadiums, where we use the hanging cables because if we use the drone with the camera, it would be deemed unacceptable because of the damage.
Well, there are two aspects here. I think you use a drone, and then somehow I think it can be very convenient too, but then somehow your drone had to communicate with the controller in our irrigation systems, say, hey, this area, but I think the drone, you're looking at the surface temperature. The difference, perhaps, when you want to see the pH value and salinity of the soil, you actually have to dig.
Yes, I was wondering if
Yeah,
that was a
that
problem.
part is the drone can give you a surface temperature, and then, hey, apparently this part of pasture are very, very dead. Okay, but then by that time it's already too late. So that's why we propose you really need a robot there to drill a hole, to take and to drill into the soil, and then to pump the pH value, salinity, and humidity, so on and so forth.
It's more stable and gives you data in advance. If you use only visual information for the drone, it's too late when you see damage, and it's much more unstable.
I think in back to if you see that the pasture is changing the color, that means you really need to do something about it, right? But in the case of doing a real-time drilling and probing the soil, just like a farmer, you go to a farm and then you dig a soil, you're looking at, you kind of twist around the soil, you try to understand what's there. It's a little bit different, but both approaches can be applied.
Okay.
Yeah.
Thank you.
Thank you.
Any more question? About 3D printing,
Yes,
you show example
yes,
to control the temperature and the quantity of
yes, go ahead.
the wire deposits in the piece,
Yes.
to build a piece.
Yes,
And
it's on this one. Or?
how do you control
Yeah, so
these
I,
two parameters?
First of all, images give you the whether you are in the right coordinates or not. Secondly, if you are in the wrong coordinates, then you have to make your CNC code, which is adaptive. And then in the CNC code, you have to make your coordinate as a parameters instead of actual values. And then in that parameters, you are filling the text file which has the coordinate. And that's how you are able to do a dynamic adjust on your CNC code.
You train a data set about different values of parameters.
Oh, that's two different things. One is thermal stress. I think perhaps that's you are asking. Is thermal stress. For the thermal stress, yes, we have to train it. Which is a paper. Maybe I can show you the paper. It's published 2019. Cyber physical system for thermal stress. Let's see what's that paper. Yes, we had to train it. We had to. Let me see the paper. I can send you the paper, but yes, we do. We published our paper 2019. So how do I know what temperature values and is okay. There's a thermal stress. I think that's probably is a good. Let me see where is so if there's a thermal stress, then the shape of your piece will be warped. I think that's one indication. So we make a piece. We make a piece like this. This is a difficult one. So this piece, if you look at not a top view but a front view, it's just like this. If you talk at the front view, so if there's a thermal stress, this is not one single line. You're going to see an angle tilted on either side, and that's causing by the thermal stress. And then so we try to use those images to train the use the CNN to train them. So how much angle means highly stressed, and this angle means a medium stress, and so on. So it is, and so we produce those data first ahead of time, intentionally to deform the workpiece, intentionally. So then, through the controlling of the temperatures, to intentionally so high stress, low stress, and medium stress. And then use those images as input to the CNN, and then the output is, okay, what is the stress level? And then if it's a good one, what should be appropriate temperature values? And then we use a control algorithm, say, hey, if it's 78, how to adjust to 75? And you can use the PID, how to gradually control your nozzle temperature. Therefore, they will reside within the 75 plus minus maybe 0.1, something like that. Yeah. So we did intentionally make the thermal stress happens, and so we have some samples which are good, some of the samples are medium and good, and not as good, and they use those to train the CNN network. Yeah. Thank you. I'll send you a paper.
Any more questions? So, I would like to thank you.
Thank you. There are many things I can learn from you. So tomorrow I'll be here, and this afternoon I'll still be here. So I'm more than welcome to chat with you.
If you want to talk with him, okay, I have some time yet. No. Okay.